Ramanujan for G is now available on the Google Play Store. Try it out for free.
Good morning, students. We started our last lecture here and we finished actually the resonance structures, about the resonance structures and what is the importance, everything we have understood in our last lecture. And later on, then we actually also see the rules for writing resonance structures, particularly what there are some rules one should keep in mind while writing different resonance structure. One is the rule number one is position of nuclei should not be changed; it should be kept fixed. So in all the resonance structures, a nuclei of any atom will not change its position. And then, but the number of unpaired electrons means the odd electrons should be same. If there is any odd electron in the molecule, its number should always be changed in all the resonating structures. Then the third rule is the net charge on all the atoms of a resonance structure must be constant throughout all the resonating structures. Means if there is a certain net charge, suppose there is zero charge on one molecule, so in all the resonance structures, there will be no net charge on this molecule. And so even if the charge separation occurs, the net charge summing up all the charges must always be zero in all the resonating structures. Or if there is an anion having a negative charge or two negative minus charge, so this charge in all the resonating structures will also be kept similar fixed, and similarly we can see for the cations as well. So the net charge in the different resonance structures are not going to change. And then the what shall we do then? The difference in different resonating structures only be in the positions of the loosely bonded electrons, and the position of loosely bonded electrons means the positions of pi electrons or the lone pairs. These are loosely bonded electrons and their positions are also the odd pair of electrons. Positions may also change, but the number of odd paired electrons must be same in all the resonance structures. Then we looked at the stability order of resonating structures, and this order is important for us to differentiate or to understand which resonating structure will be more contributing toward the resonance hybrid. And if the structure is more contributing, it means the structure is having more stability, and if the structure is more stability, having more contribution towards the resonance hybrid. So resonance hybrid will look more like this stable structure, and if it looks more like the most stable structure, so most of the reactions or the properties it will have, which will be similar to the one with the highest stability, means the one resonating structure with the highest stability. So the resonance and what are the ordered, there are different criteria on which, based on which we can determine the stability of different resonating structures. The first one is the more number of covalent bonds. If the number of covalent bonds in one structure is more, then that will be the highest stable. Then comes the atoms of all the atoms with the complete octet. If one of the resonating structure, all the atoms are having complete octet, so it will come the next. Then the more dispersal of charge. So charge, if there is any charge, net charge on the molecule, then this charge should be dispersed with more. And if it is more dispersed, so we get more stability. And then dispersal doesn't mean separation is one thing and dispersal is one thing. Dispersal means the distribution, and separation means there is nothing, but now you are separating out. So there was one thing which two things which were joined together, there was one, now you are separating them out, so to creating a difference there. So that separation of charge means the molecule is neutral, now you are creating a positive charge and negative charge on the same molecule at different places. This is the separation of the charge. And the dispersal of charge means there is a negative charge, and it is once it is on one atom, another structure it is on different atom, so it is located at different places. So in a kind of it is moving on at different places, it is distributed over different atoms, different places. This is called dispersal. So dispersal means distribution, and the separation means separating out, creating a new thing out of something else. So anyway, I hope this point is clear. And then the less separation of opposite charges. So if the separation of charges happens, means the positive and negative charges are there. In that case, the less separation of the charge means more stability. Less separation means if the positive and negative charges are at the adjacent atom or the nearby atoms. if the different structures are there and if the positive and negative charges are nearer in one of the structures, maybe in one case it is at two bond distance, in another case it is at three bond distance. Depending on that, the two bond distance, if the charge is there, or if that will be more stable, or if these charges are on the adjacent atoms, means one bond distance apart, so that will be most stable configuration. Then we came to this criteria: negative charges on a more negative atom, and usually more electronegative atom has tendency to hold the negative charge better, and so if the negative charge is on a more electronegative atom, it will be a comparatively more stable condition than the opposite if the opposite of it happens. Means the negative charge is there on the less electronegative atom. So these are the few things that you think. So if the negative charge is on the more electronegative atom, that will be more stable than if the negative charge is on a less electronegative atom. So these are things, and for few examples we have seen. Then we also saw the later on the once we understood the resonance structures and what is the resonance. And resonance, it means resonance structures means, suppose there are two resonance structures. If I am saying for these two resonance structures are equivalent, it means they are equally contributing. If you do not see any difference based on all those criteria, it means both the structures are same, and if both the structures are same, they will be equally contributing. And if they are equally contributing, so it will be easier to write the structure of the resonance hybrid, because you can distribute if the charge is there or something over all the atoms equally. So that is one thing. So resonance structure, it means all these resonating structures, as you can see here, it means these resonating structures means they are in resonance. They are in resonance with each other, and so with the resonance, they will be having some hybrid, some resonance hybrid, which is the, and with the resonance, they will forming a resonance hybrid, which is the real structure or the actual structure of the molecule, and on the basis of which you can determine all the properties of that particular molecule, organic molecule. Now, then we saw the resonance effect. And the resonance effect, we have seen two different kinds of resonance effects, which are also called mesomeric effect. And there's the first one is the plus R effect, and next one was the minus R effect. Plus R means it is a kind of electron donating effect, and it happens when a lone pair of electron is in resonance or is in conjugation with the pi system. And if the lone pair of electron in a substituent is in conjugation with the pi system, as you can see here, we see a plus R effect. So we plus R effect means it is a kind of electron donation effect, and this electron is now moving here, and it shows some resonance structures that I explained earlier, you can see here. And this, because of the positive R effect of the substituent on this benzene ring, we also see whether this is activating or deactivating. Based on that, whether it will pull away electron, push extra electron density in the benzene ring or the aromatic ring, or it will pull away electron density from the aromatic ring. Depending on this, that one can determine this substituent is activating towards the electrophilic attack or deactivating towards the electrophilic attack. Why electrophilic attack? Because this is aromatic compound having pi electrons, and so they are electron rich, and so if they are electron rich, the aromatic compounds are electron rich, there is possibility of the electrophilic attack. An electrophile which loves to get attracted, or which loves the electrons or the negative charge of the pi electron cloud, will get attracted towards it, and thus it will somewhere, wherever the electron density sees is the maximum, it will get attached to that position. And in this structure, because of the plus R effect, you can see here at this ortho position, there is a substituent, and the adjacent position of the substituent in the benzene ring is called ortho position, and then two meta positions, and the last one is called the para position. So ortho position is 2,5 position, meta position is 3,4 position. Sorry, uh, ortho position is 2,6 position. Ortho position is 2,6 position. Meta position is 1, 2, 3, 1, 2, 3, 4, 5. So 3 and 5 position is the meta position, and fourth position is the para position. Anyway, I hope you understand this. And so you see the in different resonating structures at ortho position, here and here a negative charge appears, and the para position as well the negative charge appears. So if the group is showing plus R effect, what happens? It is usually activating and the electron density is seen to increase at ortho and para positions, and so the an electrophile will attack at ortho and para position. It will get attached to these two positions. And so what is, again I'll explain, positive resonance effect is a kind of electron donation effect, and this electron donation happens in the form of donation of the lone pair, and it happens with the characteristics of molecules in which a lone pair is found to be in conjugation with the pi electron system. You see in this case. Then we show that some other examples of this is like OH, halogen, OH, this hydroxyl group, it is also having a lone pair of electrons, and if it is there on a benzene ring, it will show plus R effect. Similarly, this OCOR, this also oxygen is having lone pair, NH2 having lone pair, as you can see in this aniline structure. All the amines, primary, secondary, tertiary amine, amide, halogens, and also the alkyl groups. And alkyl groups, in the case of alkyl groups, you may not see that this transfer of a lone pair of electrons, but we see this because of the form of the hyperconjugation that we get in this case. So it shows some kind of plus R effect, some kind of a stability, pushes some electron density into the benzene ring as well. So the alkyl group also shows plus R effect. Then the negative resonance effect, which is also called minus R effect or minus M effect, or the negative mesomeric effect. And it is because if the pi electron or the pi bond associated to an electron withdrawing group is in conjugation with the another pi system. And you can see here, this is an electron withdrawing group or the highly electronegative atom. The pi electron, that is the more appropriate way to tell. If the pi electron cloud is there, or pi electron is there, or the pi bond is there on a more electronegative atom, and this pi bond is in conjugation with the pi system, then we see a negative resonance effect or minus R effect. And this is because there are two atoms, and these two atoms are bonded through a pi bond or double bond, and a sigma bond, one pi bond means a double bond. So what happens? The oxygen is having more, the electronegativity of oxygen is more than the nitrogen, and because of that, what we see, this electron, this one is being pulled by the oxygen, and so the electron density from the benzene ring is pulled away towards the substituent. So if the substituent is having a double bond or the pi one multiple bond, and this multiple bond is associated to a more electronegative atom, then we see a minus R effect working there. And because of the minus R effect, what do we see? We see a positive charge being generated at ortho and para position in different resonance structures. It means the electron density at ortho and para positions will be less. Although electron density will also be pulled away because of the minus I effect. So this group is deactivating, and deactivating it will pulls away electron density from all the positions, but because of the positive charge generation, because of minus R effect, we see positive charge gets intensified at certain positions, and those positions are ortho and para positions. So if a group having like NO2 having minus R effect, if it is attached to the benzene ring, it is called deactivating group, and this deactivating group is meta directing. Meta directing means electrophile. If electrophile will come and get attached to this ring, it will get attached to the meta position, this or this position, 3 and 5th position, 3rd and 5th position, because this 3rd and 5th position will have comparatively higher electron density than other positions. This is because of this positive charge generation in this case. So these things we have seen already in details. Let us now move into the electromagnetic effect. So the electromagnetic effect, as we have seen earlier, is a temporary effect, which is also represented as E effect. So it is a temporary effect, and this temporary effect is induced by the attacking species or the reagent. So it appears only when the reagent is there in the reaction mixture, and reagent having a particular tendency, if it is there, then only we see the electromagnetic effect. And the electromagnetic effect again is a temporary effect. It means once you remove the reagent, this effect will disappear. So the organic compounds having a multiple bond, means a double or triple bond, multiple bond means only this show this effect in the presence of an attacking reagent only. And in presence of attacking reagent only, it means this is a temporary effect. It is not associated permanently to the molecule. and then it is defined as the complete transfer of a shared pair of pi electron. In this case, we see complete transfer of shared pair of pi electrons. As we have seen in the case of resonance as well. But in the resonance, whatever the group, the substituent that is there, it got permanently attached to the molecule. It is already there in the molecule. It is the part of the organic molecule, so that effect is permanent effect. But the electromagnetic effect is not the permanent effect. A certain reagent for a certain time only get associated, get attached to the organic molecule, and so it creates that effect. And this effect will only be there till the substitute, till this reagent is there with the organic molecule. So that it is defined, this electromagnetic effect is defined as the complete transfer of a shared pair of pi electrons. So here also shared pair of pi electrons, it moves, its transfer happens to one of the atoms joined by a multiple bond. And this transfer happens to one of the atoms which is joined by the multiple bond. It means if the two atoms usually they are joined together by a multiple bond. So this pi electron will move to either of the atoms which is bound to this pi bond, and which to which atom it will move to, depending, it depends on the nature of the reagent or the attacking reagent. And if the attacking reagent is an electrophile, so it means it will, this electron will move to the atom to which the electrophile gets attached, or the reagent gets attached. So those things we will see later on. Let me first explain this. So this is again, so this complete transfer of shared pair of pi electrons happens to one of the atoms joined by a multiple bond on the demand of an attacking reagent, and it happens because of the attacking reagent, presence of attacking reagent. The effect disappears as soon as the attacking reagent is removed. It disappears, it gets vanished, and from the domain of the reaction, it is represented by E. This effect is represented by capital E effect, and the shifting of the electron is shown by the curved arrow. This we have seen the I effect, inductive effect is shown as the I effect. The inductive effect can be plus I effect, minus I effect. Resonance effect, we see it is shown as the R effect. Resonance first letter, R effect, which could be plus R, minus R. Similarly, the mesomeric effect, which is also the resonance effect, shown as plus M, minus M. Now we also see the electromagnetic effect. The first letter of electromagnetic is E. So with the capital E we show, and this electromagnetic effect is also of two types, and this is similar to other effects that we have seen. It can be a positive electromagnetic effect as well as negative electromagnetic effect. Positive electromagnetic effect is represented as plus E effect, and negative electromagnetic effect is represented as minus E effect. There is an spelling error here. Hmm. So let us now look into positive electromagnetic effect of plus E effect. The pi electron of the multiple bond in this plus effect. So what do we see? This attacking reagent could be an electrophile or nucleophile. Electrophile means it is having a positive charge, it is electron deficient center. And so if it is electron deficient center, the attacking reagent, so to whatever atom it gets attached, so it will create electron deficiency there, and the pi electron will move to that portion at that atom, and that it means in that case this effect is called plus E effect. The pi electron that is defined as the pi electron of the multiple bond is transferred. The pi electrons are, so they are transferred, means both the electrons are transferred to that atom to which the reagent gets attached. For example, if you look here, if this is the carbon double bond carbon, if the H plus proton attacks the attacking reagent, and if this proton gets attached to this carbon, so what happens? This pi electron, then both the electrons, pi electrons, the pi bond will shift to this carbon, and actually it will shift between this carbon and this hydrogen. And so this carbon, this pi bond has shifted between this hydrogen and this carbon, and so we see a sigma bond between them. And in that case, what happens? This both the electrons has moved between this carbon and hydrogen. So a positive charge will appear on this, and a positive charge we see here. And the net charge, if you see in this product and the reactant, it is same, plus 1. The net charge 0, plus 1. 1, and here we see a plus 1 charge here. So this is called a positive electromagnetic effect. It is usually happens because of the electrophilic attack on the pi system, and this is the electrophilic attack on the pi system. There can be a nucleophilic attack on the pi system as well, and nucleophilic means the electron reaches this species are nucleophile, and so if they attack on a pi system, so if the pi electrons, we see the negative E effect, so the pi electrons of the multiple bonds are transferred to that atom to which attacking reagent does not get attached. So the pi electron is there. If the Cn, this Cn goes over here, if this Cn goes over here, means it is already coming with a negative charge. So this negative charge, one lone pair, it will form the bond with this C because of this bond, and now the pi bond will move to another carbon. And as we see here, the arrow is shown in this direction. It means the Cn minus will get attached to this carbon. So this is attacking reagent, and attacking reagent here is a nucleophile, and so nucleophile, so minus T effect. And so Cn is attached here. So this electrophile, it forms a bond here, and this pi electron will move to here, and negative charge should appear on this carbon. And the net charge here in the product and the reactant is same, 0, -1, so net -1, here -1 charge you can see. So when inductive and electromagnetic effects operate in opposite directions, the electromagnetic effect predominates. And this is one important point. So there can be the inductive effect and the electromagnetic effect both happening. They both operates in a given reaction condition on a molecule. And if these effects are in the same direction, so anyway they will help each other. If they work in opposite direction means the plus I effect is towards some effect means the group is already attached, which can increase the electron density at some position, but because of the CN attack, if we show the electron density will move away from that position, so this effect will be more dominating. So anyway, these things I think very not tough to understand. This electromagnetic effect, other example we have already seen earlier, and you can see the negative electromagnetic effect in this case as well. This is a nucleophile. The positive charge, if one can understand it in a better way, the positive charge, partial positive charge is already there at this carbonyl carbon, and this CN attacks here, and this entire, this both the pi electrons, the entire bond will shift over this oxygen atom, and also a negative charge appears over here. Now let us go back to what we were looking at, and so these are the things that we have already seen. So again, this point, when inductive effect and electromagnetic effects operate in opposite direction, the electromagnetic effects predominates, because in the electromagnetic effect we see a complete transfer of electron, and a complete, and the inductive effect we see only a partial transfer of electron density, means the partial charge distribution only happens in this case of charge separation only happens in the case of inductive effect. So the electromagnetic effect predominates, wins over the inductive effect if both operates in opposite directions. Let us now look at the another very important effect which is called the hyperconjugation effect. And the hyperconjugation, as you can see, the conjugation we already know there is conjugation is the pi electron is in conjugation with another pi electron, or the lone pair, or the positive charge or negative charge or odd electron, and so on. But we see the conjugation, if there is a hyper activity, it's a excess conjugation, and that could happen if a sigma bond also gets involved in the conjugation, and that conjugation is called hyperconjugation. Hyperconjugation is the excessive conjugation, one can say. And the hyperconjugation is also the general stabilizing interaction. So this is the general stabilizing interaction with certain molecules wherever it appears. So it involves delocalization of the sigma electrons. As I said, hyperconjugation, it is named because it is excessive, or the form of the conjugation is the sigma electrons, which are usually very strong bond. Sigma bonds are very strong bond that happens between two atoms, and even if the sigma bond it gets delocalized because of the certain effect, certain thing that is already there in the molecule, then this conjugation is called the hyperconjugation. So it involves hyperconjugation, involves delocalization of sigma electrons of a CH bond usually CH bond of an alkyl group directly attached to an atom of an unsaturated system or an atom with an unshared p orbital. So this happens when the CH bond comes in conjugation with the unsaturated system. Unsaturated system is usually having double bonds, or if it comes in conjugation with the unshared p orbital. Unshared p orbital could be an empty p orbital. So comes in conjugation, and how it will come in conjugation with the shared p orbital or the empty p orbital, shared and unshared p orbital. It will come when the CH bond will come in the orientation of the p orbital, or in the orientation in which it can have certain overlap, some extent of overlap with the p orbital, whether it is empty or the complete p orbital or the filled p orbital. Sorry. So in that case, there can have, but one thing will happen: this conjugation is not that effective conjugation because it is a CH bond, and usually the CH bond will not be completely broken. And even if the CH bond is there, we'll see with the structure there will be certain constraint associated with it. So only a partial overlap of the orbitals will occur in the hyperconjugation. So even with the partial conjugation, it imparts enough stability to the molecule so that we can actually see a particular trend or predict a particular trend in different reactive species, or the whether it is intermediate or the organic molecule. So the sigma bonds that we see, the partial conjugation, it happens. So the sigma electrons of the CH bond of the alkyl group enter into the partial conjugation with the attached unsaturated system or with the unshared p orbital. So this is the partial conjugation with the attached unshared unsaturated system. The unsaturated system which it attached, or the p orbital, the two, this is the unsaturated system. Two of your orbitals will already be there, which will be interacting with each other. And now the sigma bond starts interacting with this p orbitals, filled p orbitals. Or in the case of carbocations or the empty p orbitals, what we see, this will be unshared, and it will lie actually perpendicular to the plane of that carbon center. And so if the certain bonds come while rotating in this orientation, the CH bond, then it can also overlap with this empty p orbital, and so we see this effect. The hyperconjugation effect is also a permanent effect. And why it is permanent effect? Because it is already there because of one group that is already permanently attached to the molecule, or it is a permanently part of the molecule or the intermediate or any chemical species. Let us consider the example of this ethyl carbocation, and this ethyl carbocation in which the positively charged carbon atom has an empty p orbital, and this carbon atom to which this positive charge is there, there will be an empty p orbital that I have already seen, and you know this as well. One of the CH bonds of the methyl group can align in the plane of this p orbital, and the electrons constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital. What does it mean? It will be more clear with this figure. So there is a positive charge on this carbon. This is the carbocationic center, and this CH bond, and this CC bond will be one plane, and this p orbital will be perpendicular to the plane of this plane, this carbon carbon H H. This p orbital will be perpendicular to this. Now this carbon is having three CH bonds, and this CC bond is freely rotatable. As we know, there it can exist in different uh, there can be different conformations, and the single bonds are freely rotatable, and they rotate freely at room temperature because of the certain kinetic energy associated with the molecule. And once this bond rotates over in a certain position, what will happen? This CH bond, or this CH bond, this hybrid orbital, sp3 hybrid orbital, will align in the direction of this p orbital. Once it aligns with the same orientation with this p orbital, there will be some partial overlap between them, this and this two orbitals. So this is empty p orbital which will overlap in this orientation with the sp3 orbital, and this sp3 orbital which is nothing but of the C sp3 H sigma bond. And so it will the overlap will happen here. Once after some time, what will happen? It will again rotate in certain directions. Then another CH bond will come and it will align in this direction, and will overlap with this. Then and third CH bond can also, while rotation, come and align along this direction in the orientation of this, and there can there can happen a partial overlap. So this is how we see the empty 2p orbital of the carbon is there, which can be in the particular orientation of the CH bonds, and this angle there can have a partial overlap between them, which is called hyperconjugation. And the one thing why this CH bond is not overlapping with this empty p orbital, because this CH bond is perpendicular to this TP orbital, and when they are perpendicular, there will be zero overlap. So one is in this plane, and this p orbital is low, and the larger portion of this orbital will be above the plane and below the plane. This plane there will be no, so there will be no overlap. And so the one of the CH bonds of the methyl group can align in the plane of this empty p orbital of this carbon atom, and the electron constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital, then the electron is delocalized into the empty p orbital. This type of overlap stabilizes the carbocation because electron density from the adjacent sigma bond helps in dispersing the positive charge. So once the overlap happens, some of the electrons or the electron density will get transferred to this center, this p orbital. It means this positive charge which was localized over this carbon atom now will delocalize, it will disperse to a slight extent on this carbon atom as well, this orbital as well. And so once the dispersal of this positive charge will happen, the stability will increase. Another point that is important to understand here is why there is a partial overlap. As we see in the case of p orbitals, the two p orbitals they come in with the same orientation, they align along with each other in the same direction, in the same line. Then we see there is a significant overlap. We do not see a partial overlap in that case. It means suppose this was also a pi p orbital, this also p orbital, both are along the same axis, so there will be a significant overlap. In this case, why we are saying partial overlap? This is because of the geometrical constraint. And this geometrical constant is because this carbon, this orbital of this carbon is sp3 orbital, and the sp3 orbital, so there is an angle of around 109 degree between this bond and this bond. And if this bond and this bond were at 90-degree angle, so there can have a significant overlap between them. But this angle is not only 90 degree, it is more than 90 degree and more than 90 degree. And this lobe you see on this side is a very small, so it will not overlap with this. The overlap will only happen in this region, and that overlap because of the angle that is there around 109 degrees, a partial overlap only. And the hyperconjugative structures can be written in this presented in this form. Although we see there is a only partial overlap, as you can see here, and with the partial overlap, we cannot show a complete transfer of electron here. But to represent this structure, just for a representation purpose, one of this is the structure one can write of this ethyl carbocation. In another, this structure represents one of the hyperconjugative structure of this ethyl carbocation. And this structure, what we are showing that this sigma bond has is got transferred between this carbon and this carbon, and with the p orbital, so one can show a double bond here. So a kind of this is a kind of it means this bond is shifted between this carbon here, and thus a proton, a positive charge on this H plus will appear. Then in another structure, we can see the similar thing between this CH bond and this CC. So what happens? This CH bond now then the next time this will get transferred between this carbon atom, and so a positive charge will be there on this proton, and in the third case this will have a positive charge, and you can see this in this structure. So based on this, there can be three hyper conjugative structure of this molecule. This is one hyperconjugative structure, this is another, and this is another. So there are three hyperconjugative structures of ethyl carbocation. And if the number of hyperconjugative structures are more, it means that carbocation or that species will be more stable. So the number of the hyperconjugative structures will determine what will be the relative stability of a given molecule. Now let's see. So in general, the greater the number of alkyl groups As you see, if there is only one methyl group, we see three hyperconjugative structures. If there was another methyl group, this CH3, well, if it is also replaced with another, this hydrogen is also replaced with another CH3. So because of that CH3, three CH bonds are there, we could have another three hyperconjugative structures. And if this H was also replaced with another CH3 group, so we could have another three hyperconjugative structures. So if the number of the alkyl groups is more to this carbon and then attached to this carbon, then the number of hyperconjugative structures will also be more. So in general, greater the number of alkyl groups attached to a positively charged carbon atom is a carbocationic center, the greater the hyperconjugation interaction or the hyperconjugation structures and the stabilization of the carbocation will happen. And you see the carbocation is now more, this positive charge is dispersed over more atoms, and more the atoms it is dispersed over, we get more the stability. And that is why we have the following relative stability of carbocations. This relative stability we have seen, we also see because of the plus I effect. Plus I effect, this is plus I because this group shows plus I effect because of plus I effect. It somehow it decreases the electron density here, all the three groups. Apart from this, if you remember, I said that it gets also help from the hyperconjugative structures, and we see the number of hyperconjugation will be maximum in this case because three CH3 groups are attached to this carbocationic center, and we cannot not have more than three CH3 groups attached to this carbon center because it has a positive charge, and it means it can have only three substituents attached to it only. So the nine hyperconjugation structures, in this case it will be more stable. In this case, this is two substituents, CH3 substituents, only methyl substituent attached to this carbocationic center. So 3 into 2, 6 hyperconjugative structures will be there. So 6, and this is the, having only 3 hyperconjugative structures, and this structure CH3 plus will have no hyperconjugation because it is only the hydrogen atoms are there attached to the carbon, and all those CH bonds will be in one plane, and the p empty p orbital will be perpendicular to that plane, and so there will be no uh, overlap, partial overlap between CH sigma bond and the empty p orbital, and thus there will be no hyperconjugation structure in this case or hyperconjugation interactions in this case. So hyperconjugation is also now, so this is what we see because of the now the hyperconjugation wins over the plus I effect. So this stability determines mostly based on the hyperconjugation effects. Now we also, as we have seen earlier, hyperconjugation is also possible in the case of saturated compounds, means the alkenes or alkyl arenes. Alkyl arenes means the benzenes. Example is benzene substituents or the alkyl benzenes, and the delocalization of the electrons by hyperconjugation in the case of alkenes is shown here. And what do we see here in the case of alkene? We see a carbon-carbon double bond. This is the pi bond. So this was the sigma bond. This is the sigma bond. We see a pi bond perpendicular to the sigma bond, and there is overlap, double wedge overlap in this two wedge overlap in this pi bond. And when once this p orbital, the field p orbital, or the both orbitals are having one electron, you can say having one electron. Once this CH bond, which is freely attached to this carbon atom, and this bond is anyway freely rotatable, and so once it comes in the particular orientation where it aligns with in the direction of this p orbital, which is already shared with having sharing out, which already having overlap with another p orbital of the adjacent carbon in another direction. But we still see some overlap, and in anyway, any where if the overlap happens between two orbitals, we get more stability. And this more stability we can also understand in terms of what if there is overlap. So more electron density will be shifted between these two carbon atoms, and more electron density is shifted between these two carbon atoms means there will be less nucleus repulsion between them because the electrons will come and it will intervene the interaction between them. And so because of that we see the stability in this case. If the electron repulsion is diminished, sorry, nucleus or internuclear repulsion is diminished, then what will happen? The repulsion increases the energy of the system, and so the and if it is decreased, the repulsion decrease. So what will happen? The energy of the system will go down, and so the system will get stability. And that is why even the pi systems like the alkenes that you can see here, this is CH3, CH2, CH2, means it is a propene. The propene, in this propene we see some stability is obtained because of the hyperconjugation. And similar example you can also see for the toluene when the CH3 group is attached to the benzene ring. So there are various ways of looking at the hyperconjugation effects. One way is to regard the CH bond as possessing a partial ionic character due to resonance, and that partial ionic character we see here. If you look at the ionic character on this hydrogen atom or the CH bond, so we will see there are four structures, and out of the four structures, this is having one positive charge, so 1 divided by 4, so plus 1 by 4 charge, net charge, one can assume maximum plus 1 by 4 charge on this hydrogen, similarly on this, and similarly that will happen on this carbon atom as well. Although that charge distribution, the plus charge distribution is not same between this and this structure, it could be same in this three structure, but that is not same in this. But one can assume to show this to show the hyperconjugative structure. So one way to show the various hyperconjugation structures is to regard the CH bond as possessing a partial ionic character due to resonance, means the hyperconjugation. And that resonance you can see this is a propene molecule, and this propene molecule, this CH bond, as we see, if it gets aligned in the direction of the p orbital of this carbon atom, so what will happen at this bond will shift between them, and one may assume that there is a double bond between this carbon and this carbon atom, and so this sigma bond shifts between these two, and so this pi bond, this once a double bond forms here, this pi bond, a negative charge will appear on this, a positive charge over here, and thus we also get a more number of structures that appears for this molecule. Similarly, once this bond will shift in this bond will shift between this carbon atom, and so we see this structure. In third case, this bond will shift between these two atoms, and we see this structure. So these are the hyperconjugation structures, or hyperconjugative structure, and this hyperconjugative structures stabilizes any molecule, so it is in general an stabilizing effect. Thus, hyperconjugation may also be regarded as no bond resonance, and why it is regarded as no bond resonance? Because once you can see here, there is no bond, but there is no resonance here. So this is no bond resonance. The resonance with the and there is no bond. The resonance is here, and anyway. Now let's see this question. Now I hope this is clear to you. And because of this structures, this region only, the hyperconjugation is called no bond resonance. I hope it is clear. As you can see, the no bond resonance in this structure resonance, there is a structure and resonance, and we see a no bond between uh, C and H atom in one of few of the hyperconjugative structures. Let us now see this question. Explain why this tertiary carbocation is more stable than this primary carbocation and the methyl carbocation. The reason I have already explained here: primary, tertiary carbocation, secondary carbocation, primary carbocation, and methyl carbocation. The reason already explained here, because this tertiary carbocation will have 9 hyperconjugation conjugative structures. 9 hyperconjugative structures. Why? Because one CH3 can form 3 hyperconjugative structures, and there are 3 CH3 groups. So 9, 3 into 3, 9 hyperconjugative structures will be there for this molecule. For this molecule, there is only one CH3, only 3 hyperconjugative structures, and in this case, there is 0 hyperconjugative structures. And so this will be least stable. So in CH3, the vacant p orbital is perpendicular to the plane in which CH bond lie. Hence, it cannot overlap with it, means the p orbital cannot overlap with the CH bond, and thus CH3 lacks hyperconjugation. This reason was already explained earlier. Now let us look into the types of organic molecules. So all the effects that was required for us to understand, that is already explained. Now let us look into the types of organic reactions. Then we look into the methods of purification of organic compounds. The types of organic reactions I will explain only briefly here, because all these reactions we will see in details when we will see reaction reactions of organic compounds. So all these details examples we will see later on, but I will explain it briefly here. And these methods of purification of organic compounds I will explain in the next class. Let us now look into the types of organic reactions. So there can be four different types of organic reactions. So the organic reactions can be generally classified into four different classes. One is called substitution reaction, then the addition reaction, then elimination reaction, and the rearrangement reaction. If you understand the meaning of this term, substitution, addition, elimination, rearrangement, you will also know the definition of what these reactions. But the substitution means there is already something and you are substituting it with something else. So if an organic molecule is there and already there, and if in that organic molecule an existing group is substituted by some new group, then that reaction, such reactions are called substitution reaction. And the example you can see, the alkyl halide CH3I is there, and if Cn minus attached to this, and if C formation of CH3 Cn, and this I minus will leave as a living group, and so this is a substitution reaction. So anyway, substitution reaction means one group is substituted from some new groups, and so it is substitution. And this property of the substitution reaction could be different types of organic compounds. As you see, the substitution is happening. Why one group has which is coming here and it do not get permanently attached to it? Why a substitution is required? Means another group will leave after this group has attached to the organic molecule, and this happens because if the organic compound is a saturated compound, if it is already saturated, and if it is saturated means all of the four valencies of carbon is already complete. Now if you add some extra bond, if you add some extra group and extra bond is formed, but that group, that configuration is not that stable because carbon cannot expand its valency. So what will happen in some of the group which is either will depart away from this carbon center, and that group will either having a very strong tendency to uh, live separately, or at least have a strongest tendency among all the groups attached to that carbon to be alone, or what else will be the weakest bond will be broken out. So a new bond is formed and there are four already existing bonds. So which bond will be compensated for this new bond? The one with bond which is least stable and having least bond energy or least bond dissociation energy. So that if that bond is broken, then very small amount of the energy will be required. This is one thing, and another thing is after that bond is broken, what will happen? A new charge species or new species will be formed, and that species was not very stable, and that is why it was there with the carbon and forming bond. And so if that species is not very stable even in the isolated form, so the solvation of that species also matters, or the stability of that species in that form. And so the substitution, and we see the substitution reaction. So mm, occurs because of that one bond form, another bond is broken, and this substitution reaction can be of two types: nucleophilic substitution and the electrophilic substitution. One reaction that I have explained you is the nucleophilic substitution reaction, because the nucleophile means electron rich species has come, and one of the electron rich species will depart away from the system, and the one bond which is least stable, and one species which when departs away gives most stability, or gives less most stability to the entire system. So the nucleophilic substitution reactions are the usually properties of the saturated compounds, and these saturated compounds, but they also have the nucleophilic center. It means the carbon must be one of the carbon in those compounds must be associated with or linked with a very highly electronegative atom. Then only a nucleophilic center will be generated there, so that a nucleophile gets attracted towards that center. And the example of the alkyl halide, as I said, alkyl halides are having very high electronegativity. The fluoride, bromide, iodide, and the fluoride, they are having high electronegativity. Because of that, a nucleophilic center will be generated. Or even if the hydroxyl group is attached to a carbon center, the hydroxyl group, because of the high electronegativity of oxygen, that will be positive center. And if this carbon center is anyway already saturated, means all the four valencies of carbon is already completed by four different groups. There is no carbon-carbon double bond or carbon heteroatom double bond. Then that is what the saturated compound. There is no carbon heteroatom double bond or carbon-carbon double bond. Then we see the electrophilic substitution reaction. Then another kind of substitution reaction. Electrophilic substitution reaction means the attacking species here will be the electrophile, and the electrophile will get attracted towards only the electron rich species. And what could be the electron rich species or electron rich organic compound? It could be the pi electron system, and the pi electron system, but that substitution should also occur there, and that is what we see. This electrophilic substitution reactions are the properties of aromatic compounds, because aromatic compounds are anyway, their pi electrons are there, they are pi electron rich species, so the electrophile gets attracted towards it, and electrophile once get attached to the aromatics group one of the carbon of the aromatic compound. What happens in that case? Then what happens? The aromaticity dis gets disturbed, and if once the aromaticity gets disturbed, the system becomes unstable. And so, in order to regain its aromaticity, some of the groups, one group will depart away from the system, and that is why it is called the substitution. So, it calls substitution. So, electrophilic substitutions are the properties of the aromatic compounds. Why aromatic compounds? Because once the electrophile comes and get attached, to gain that, it disturbs the aromaticity, and to gain the aromaticity, the group which was previously attached to that carbon center before the attack of the electrophile, that will depart away from the center, that carbon center, and so it will again regain the aromaticity, and so this reaction happens. Then the second type of reaction is the addition reaction, and where the addition can happen. Addition can happen at the saturated bond position. And the saturated bond position, so there is a carbon-carbon double bond or carbon heteroatom double bond. And the carbon-carbon double bond or carbon heteroatom double bond means the two groups will be attached to this double bond at two different centers along which the double bond is there. But in that case, a double bond or the triple bond, we can also say that triple bond means unsaturation is there. So in that case, what happens? This reaction could also be the nucleophilic addition or the electrophilic addition. The nucleophilic addition means the attacking species. This reaction is now initiated by the attack of the nucleophile. Then it is called nucleophilic addition reaction. So nucleophiles trigger this reaction, addition reaction. So nucleophile will first go and get attached to one of the center, nucleophilic center of the compound, and then the what happen, a nucleophile is anywhere is the electron rich species, and now that pi bond will shift to another carbon atom or another atom, the if it is heteroatom, to the heteroatom, and so another group will get attached, the positive charge center will get attached, and so the addition will happen. And this kind of compound nucleophilic addition, one can see it can happen in the case of carbonyl compounds like C double bond O. This is one example. The nucleophilic attack can happen. The nucleophile will come. It will, the electron rich species, it will get attached to the carbonyl carbon because it is a nucleophilic center having some partial positive charge. And once the nucleophile comes, the pi bond will shift to the oxygen atom, which can abstract some other group or maybe H plus from the water or another solvent if it is possible, or some other group, and an addition will happen to the carbonyl bond. Now there's another form is the electrophilic addition reaction. An electrophilic addition reaction means the electrophile will be there. It means there is this center, the organic molecule must be the substrate must be having a double bond, or the file rich system, and then the electrophile means like H plus, as we have seen earlier. The proton comes there, and now protons is initiated by electrophile, means the electron deficient species. And so another group now will get attached to the another carbon atom, because once this electron deficient species, this electrophile file gets attached to one of the carbon atom, it will pull away this attachment, this linking happens with the shifting of the pi bond. And once the shifting of pi bond happens, another carbon will attain some positive charge, and so some electron species from this, particularly if the water reaction is happening in water or some other alcohol or some other group, there's a solvent will go, and the solvent may also go and get, because of the presence of lone pair we get associated, to the addition will happen. Now let us look into the elimination reaction. As you can see, elimination reaction will be opposite to the addition reaction. Addition elimination means removal of this group, and the addition is the elimination is opposite to the addition. And this, as we see, the addition happens, two groups get added to an unsaturated center, and in elimination what happens, two groups will be departed from. It can depart from the same atom or same carbon atom or the adjacent carbon atom. If both the groups depart from the same carbon atom, which is also called geminal center, and not only the same carbon, any other atom, any center, any atom, then it's called alpha elimination, because both the groups are broken away from the same carbon center, and is called alpha elimination. Or the geminal carbon center, alpha means the geminal carbon atom, depart of one of two groups happens from the departure of the two groups happens from the same carbon atom, or same atom of any, if it is a heteroatom, then it is called alpha elimination, and the beta elimination is the two different groups that depart, or two groups depart from the adjacent carbon atoms, or the adjacent atoms or the bonded atoms, and those adjacent bonded atoms, two different groups depart, is called a beta elimination, and this adjacent centers are also called vicinal centers. So the two groups will depart if they depart from the vicinal atoms or the carbon atom, then such elimination is called beta elimination. Then comes the rearrangement reaction. This rearrangement reaction, as we have seen, like in one kind of electromagnetic effect, that the kind of electromagnetic effect is also a kind of rearrangement that we see, rearrangement of the bond. Rearrangement means the rearrangement of a particular bond. The pi bond has shifted to somewhere else. So some reagents trigger some kind of rearrangement of this, and the molecules rearranged itself, not only reagents. Some conditions also facilitate the rearrangement between these molecules. So in the given conditions, maybe at higher temperature or in the sunlight or something, what happens? This molecule is not that stable in that form. So it will rearrange in such a way that it gets stability at a given temperature. And such reactions are called rearrangement reactions. So rearrangement means already one substituent is at one position, now it will go to some other position, so that in the given condition the molecule or the any chemical species gets a stability. And one example of the rearrangement is we see in the migration of methyl or protons in the case of carbocations. The carbocations are formed as intermediate inorganic reactions, and if that carbocation is not sufficiently stable, and if with the migration of any group we see the possibility of the increasing of the carbocation, possibility of the increase in the stability of the carbocation, it means if by rearrangement of or by transfer of methyl or any alkyl group, if we see the primary carbocations become secondary or tertiary carbocation, in that case that rearrangement will happen, and so we see the rearrangement reaction there. Now the methods of purification of organic compounds we'll see, which I'll do in our next lecture. Okay, bye. I'll stop here.